of reactions that we need to learn how to predict the product for are my personal favorite, the combustion reactions. In all honesty, the most difficult part of predicting the products of a combustion reaction is recognizing that you're dealing with a combustion reaction. At first glance, they tend to have the appearance of a single replacement reaction because they're going to contain a compound and an element. However, combustion reactions are unique because the compound is always going to be something organic, meaning it's going to contain carbons, hydrogens, and every now and again, the occasional oxygen. That organic molecule is always going to be reacting with O2 as the other reactant. If you can recognize that, then predicting the products is going to be a breeze because the products of a combustion reaction are always, always, always carbon dioxide and water. This is one of the few reaction types where the reactants are covalently bonded instead of ionically bonded. And what that means is that you can end up with some compounds that are pretty big, some really, really, really large organic compounds with some pretty large subscripts. However, it does not matter how big that organic molecule actually is. They will always, always combust to form carbon dioxide and water. For example, if I were to take something like C3H8, or what we would call propane, and combine it with oxygen, we could recognize this as a combustion reaction because we have some carbons and hydrogens, thus the organic component here, reacting with the oxygen or the O2 gas. In this case, to predict the products, all we have to do is recognize that the products never change. The products are always carbon dioxide and water, without fail. Even if we were to do something as wildly big and complicated as C8H18, maybe, and react that with oxygen, it still doesn't matter. Regardless of how big or complicated or ugly this organic molecule actually is, the products are always the same. Carbon dioxide and water. The trickiest thing with these is probably balancing them, simply because there's so few elements and so many compounds. Every now and again, we can run up into a little bit of a hiccup with these where we have to end up doubling all of our coefficients in order to get rid of some odd numbers. But frankly, those are kind of few and far between. Regardless, if we wanted to take a look at balancing these, here's how we would do it. I would still follow my same order here of balancing my metals, nonmetals, hydrogens, oxygens. We don't have any metals. We could start with carbons here. By doing this, we would need a 3 for the CO2 to balance our carbons, a 4 here for the water to balance out our hydrogens, and then a 5 here for the O2 to balance out our oxygens. Now, in the example I was talking about a second ago, or in just a moment ago, when I was talking about how sometimes we may need to double some coefficients in order to cancel out some halves and odd numbers and stuff like that, this second example is a pretty good indicator of that. So I do want to walk you through this one here, since predicting the products is pretty easy. With our carbons and hydrogens and oxygens, again, I think it's extraordinarily important that we first take inventory. This reaction starts with 8 carbons, 18 hydrogens, and 2 oxygens. Over here on my product side, I have 1 carbon, 2 hydrogens, and 3 oxygens to start. So if I start following the same method that I have before, I would first start by fixing my carbons. 8 go in, only 1 comes out, so I can fix that by putting an 8 here. It does change things around pretty considerably here. It does change my carbons, but it also changes my oxygens. I want to make sure I recount from 0. This now gives me the 8 carbons that I need, but as far as oxygens, I now have 8 times 2 to give me 16, and one more here gives me 17 oxygens. It's already off to some pretty big numbers. No reason to panic, though. Trust the process. If I then move on to my hydrogens here, I'll see that I have 18 hydrogens that went in and only 2 that come out. To fix that, I'm going to need to put a 9 here in front of the water. 9 times 2 would give me 18 hydrogens that I need, but it's also going to change my number of oxygens again. So again, I start from 0 and recount. This does give me the 18 hydrogens that I was looking for, but let's take a look at these oxygens now. I have 8 times 2 here to give me 16 oxygens, and I also have 9 times 1 here to give me 9 oxygens from the water. Well, 16 plus 9 gives me 25 oxygens. Now, here's where this becomes a little bit of a conundrum. If I look over here with an odd number of oxygens, and if I look over here on my reactant side in order to balance it, there is no single whole number that I can put in the blank here that would give me 25 oxygens. Any number that I put here is going to multiply by 2, and any number that multiplies by 2 is an even number. Well, we can actually use that little math rule there, that little trick, to our advantage here. If we could change the numbers here to end up with an even number of oxygens, then we could still balance this equation. Well, a pretty simple fix would be to double everything that went out of this reaction and then fix the reactants as a result. So here's what I mean. Again, we only need to do this when we can't put a whole number here. Remember the 25 that's here, though. It's going to come back in a minute. So let's double what we have so far. I had 8. I'm going to double that to 16. I had 9 here. I'm going to double that to 18. Now, that is going to change our numbers here, and that's okay. This now gives me 16 carbons, 36 hydrogens. That's a lot. And trust me on this, 50 oxygens. Or, in other words, basically double everything that I had there originally. So if I go back over here to my reactant side now and try to fix this thing, there's just a couple of things I need to do. First of all, you'll notice that my carbons and hydrogens are now half of what they need to be. So a simple fix to that is to put a 2 here instead. That's going to change my carbons and hydrogens to 16 and 36 respectively, which is great. But I'm still stuck with this oxygen here. But at least now I also have an even number of oxygens. So what I need is a number that'll go in the blank here, multiplied by 2 to give me 50. If you remember, I said to remember the number that was here a minute ago. That number was a 25. If I put a 25 in that blank, that gives me the 50 oxygens I need. So anytime we end up with this weird situation where we seemingly can't put a number in a blank in order to balance it, especially with these combustions, a good little trick is just to simply double everything. Now again, yes, this is a video about predicting the products of a combustion reaction, but I thought it was worth at least walking through the balancing of one of the trickier ones here. The biggest key takeaway from this is that the hardest part of predicting the products of a combustion reaction is just recognizing when you have one in the first place. Be on the lookout for the carbons, hydrogens, and the occasional oxygen reacting with O2. If you can spot those, then you can rest assured that your products are always CO2 and H2O.